In this video, we are going to learn about matrices and how they are applied to linear algebraic equations. We will only be showing concepts briefly and generally. There will be no attempt to prove matrix properties. All of the details you will encounter in your Physics 122. In this course, we'll learn only what we need about matrices. A matrix is a rectangular array of elements represented by a single variable. Each element of a matrix is an element of a row and a column. In this slide, the matrix elements are arranged with two subscripts. The first subscript corresponds to the row where it is found, while the second subscript corresponds to the column where it is found. If a matrix has n rows and m columns, it is called an m by m matrix. If a matrix has only one column but n rows, it is called a column matrix. If a matrix has only one row and m columns, it is called a row matrix. If there are equal number of rows and columns, the matrix is called a square matrix. Here are different kinds of matrices. A symmetric matrix is a matrix where the elements are a mirror image along the diagonal. The axis of symmetry are the diagonal elements. You can clearly see that the elements of the lower triangle is a mirror image of the elements of the upper triangle along the diagonal. A lower triangular matrix has non-zero elements below the diagonal, including the diagonal elements, but has elements of 0 in the upper triangle. This is the reverse case for the upper triangular matrix. A diagonal matrix is one where only diagonal elements are non-zero. If these diagonal elements are unity, it is called an identity matrix. The banded matrix is a matrix where the diagonal elements and the elements of its next adjacent upper and lower diagonal have non-zero elements. This is commonly found in quantum mechanics, as you will see in your future courses. You can add and subtract matrices together as long as the two matrices have equal dimensions. The addition and subtraction of matrices are commutative as well as associative. You can also multiply a scalar quantity to a matrix. Each element of the matrix will be multiplied by the scalar number. Matrix multiplication, on the other hand, is not as simple. If matrix A is to be multiplied to a matrix B, matrix A should have the same number of columns as rows of matrix B. In summation notation, each element of the product matrix C can be computed using the given notation. Matrix multiplication is associative and distributive, but not commutative. In general, the product of the matrices A and B is not equal to the product of the matrices B and A. If a matrix is square and non-singular, then we can define the inverse of the matrix. The trace of a matrix is obtained by simply taking the sum of the diagonal elements. The transpose of a matrix involves replacing its rows into columns and its columns into rows. In other words, the row subscript becomes the column subscript, and the column subscript becomes the row subscript, as shown in the example. There is also what you will call the matrix determinant. Symbolically, the determinant of A is written as two vertical bars around the matrix variable, or simply write det A. For a 2 by 2 matrix, the determinant is obtained by simply multiplying the diagonal elements together and then subtracting from the non-diagonal elements as shown, A11 times A22 minus A21 times A12. For a 3 by 3 matrix, first select a row or a column. Beginning with the first element of the row or column, which in this case is A11, cross out the elements along the first row and the elements along the first column. We are then left with 4 elements, which we call the minor. We call A11 the cofactor. You multiply the cofactor with the determinant of its minor. Here's the cofactor, and here are the minor, and you get the determinant of this minor and multiply that with a cofactor. Then you identify the second set of cofactors and minors. The second cofactor is A12. Cross out the first row and the second column, then you are left with its minor. Multiply again the cofactor by the determinant of its minor and subtract this from the first result. So this is your cofactor, and these are your minors, A21, A31, A23, A33. Get the determinant and multiply it by the cofactor, A12. Then add the third cofactor, A13, multiplied by the determinant of its minor, identified by crossing out the first row and the third column. In this example, the cofactors are row elements. You can also use column elements as cofactors. We list down a few determinant properties. The determinant of an identity matrix is 1. The determinant of the transpose of the matrix is equal to the determinant of the matrix. The determinant of the inverse of a matrix is the same as the reciprocal of the determinant of the matrix. The determinant of the product of two matrices is the same as the product of their individual determinants. The determinant of the product of a scalar and a matrix is the same as the product of the scalar and the matrix determinant. Now let's see how this is implemented in MATLAB and Python. Let's take a look at how matrices are implemented in MATLAB. The first thing that you need to do is to create a matrix. If we have a 2 by 2 matrix, we create them by typing them in like this. So A is equal to 3, A is equal to, open square brackets, 3 space 2 semicolon minus 1 space 2 close square brackets, and then you end up this whole statement with a semicolon. The space separates elements from each row, and the semicolon separates elements from each column. Okay, so if I create another matrix M, I have 1 space 4 and then semicolon and then 3 space 5. These two matrices creates a 2 by 2 matrix. If you want to create a row matrix, you simply type in 5 space 7. If you want to create a column matrix, you simply type in 18 semicolon 2. The semicolon tells MATLAB that 2 is another column. If you want to create a unit matrix, that is an identity matrix, the command that you're going to use is I. Whatever the number is inside this command tells you the size of the matrix. So if I type in here 3, then I get a 3 by 3 identity matrix. If you want to check the dimension of A, you type in size A. What this does is it will tell you what kind of matrix it is, how many rows and how many columns. So this is a 2 by 2 matrix. It has 2 rows and 2 columns. In order to determine the number of elements in the matrix, you use the command numel A, short for number of elements. So numel A will give you 4 elements because it's a 2 by 2 matrix. So if you want to determine the number of elements in the largest dimension, what you do is to use the command length. Length, in this case, if you type in length of A, we'll get an answer of 2. But if you have, for example, a 3 by 2 matrix, and you type in length of that matrix, then it will give you 3. Or if you type in a 2 by 3 matrix, it will still give you 3 because it only returns the largest number of elements in any dimension. If you want to call on any element, what you do is to type the name of the matrix, and then type the element number here. So in MATLAB, the minimum index is 1. So the first element is 1, 1. The second element in the first row is 1, 2. The second element in the first column is 2, 1, and so on. In order to add or subtract matrix, you simply type in the command for addition and subtraction. Here are the examples of allowed matrix multiplications. So A is a 2 by 2 matrix and C is a column matrix. 2 by 2 matrix and a column matrix is allowed. A is a 2 by 2 matrix and M is a 2 by 2 matrix as well. This is allowed because it has the same number of rows as the number of columns in M. B times A is also allowed. B is a row matrix and A is a 2 by 2 matrix. B has 2 columns and A has 2 rows. M times A is also allowed. As you recall, M is a 2 by 2 matrix and A is a 2 by 2 matrix as well. However, A times M is not equal to M times A. So A times M has that value is not equal to M times A because the matrix multiplication is non-commutative. The inverse of matrix A is written as this: INV open close parenthesis A, and I assign that to the variable W. Now W, which is the inverse of A times A, should give us the identity matrix. So W times A, you have the identity matrix. The trace of a matrix is determined by simply typing in this command: trace open close parenthesis of A. So we type in trace of A, we get 5 because A has 3 plus 2 3 and 2 as diagonal elements, so the trace is 5. The transpose of a matrix is written as this: you have a single quotation mark next to the variable which you want to get the transpose of. To get the determinant of a matrix, you simply type det A. Okay. So det A is equal to determinant A. And if A is equal to 3, 2, negative 1, 2, its transpose is equal to 3, negative 1, 2, 2. To get the eigenvalue and the eigenvector, simply type EIG of A. V is the eigenvector and D is the eigenvalue. Here are some examples of matrix multiplications that are not allowed. Okay. In order to run this, you have to remove the comments by clicking here. You can download this script from the VLE. Now let's take a look at how to implement matrices in Python. So before you begin, you need to import these two libraries, the numpy library and the scipy.linalg library. You assign that to the pointer np and this to the pointer la respectively. So to create the matrix, you simply type np.array open close parenthesis, and then the first row is enclosed in square brackets. The second row is also enclosed in a square bracket, and each column is separated by typing in this comma. Okay, so this is your first row. Type in a comma to get to the second row. So this becomes your second row. In the same way, if I want to create the matrix M, I type in np.array open close parenthesis and then open close square brackets, and then the first row I enclose in a square bracket. I type in a comma to tell Python that I want to go to the next row, and then open close square brackets for the second row, and so on and so forth. This creates a row matrix, so I simply separate it by a comma. This creates a column matrix. So I enclose the first row with a square bracket and the second row with another square bracket and separate each row by this comma. To get the identity matrix, I type in np.identity open close parenthesis 3. This number tells me the size of the matrix. So this is a 3 by 3 matrix. To check the dimension, I type in len A. This will give me the number of rows. And then I type in len a of 0. Okay, this will give me the number of columns. In Python, the lowest number of index is 0. So what this does is it's calling on the first row. So what is the length of the first row? And that will give you the number of columns. Okay. Alternatively, instead of doing all of these, you can simply type in a.shape. So if we go to the console, we type in a.shape, where a is your matrix that you want to get the dimension of. Okay, so of course I have to run this first. Okay, then a.shape, then I get a 2 by 2 matrix. If I want to determine the number of elements of matrix, I type in size of A, np.size of A. Recall that size is different in, the size command is different in MATLAB. The size command determines the number of elements, so it's actually equivalent to the shape command in Python. Okay, the len of A is just the same as the length of A in MATLAB. It returns the number of elements of the largest dimension for any matrix. If you want to call on a matrix element, you type in A, open close square brackets, and then you type in the index number. Remember that in Python, the index starts from 0. So that means that A11 in your matrix is A, open close square brackets, 0, 0 in Python. So A, 0, 0 in Python will give you 3, which is the A11 element in the matrix. Matrix addition and subtraction is the same. So A plus M and then A minus M. And then if you want to do matrix multiplication, this is how you do it. So A, and then you use a dot symbol, and then you use the dot command, and then type in the second multiplicand. So A times C. This is what it means. This is also A dot M, this is B dot A, and this is M dot A. Again, A dot M is not equal to M dot A because multiplication is matrix multiplication is non-commutative. Okay. If you want to get the inverse, this is the command that you're going to use. np.linalg.inv of A. If you want to get the trace, this is the command, np.trace. If you want to get the transpose, you use np.transpose of A. And if you want to get the determinant of the matrix, you use np.linalg.det of A. Finally, if you want to get the eigenvalue, you use la.eig of A. One of the applications of using matrices is solving linear algebraic equations. If you have m equations with n unknowns, as shown in the top, they can be written in matrix form as shown in the bottom. Here are the coefficients, here are your unknowns. The task of solving for x sub I then becomes much easier once you apply your knowledge of matrix mathematics. Let's consider two equations with two unknowns as shown. A typical method in determining x1 and x2 is to graph both equations in the x2 versus x1 axis. Since these two equations are linear, you can graph two lines and determine their intersection. The coordinates of the intersection are the solution. In this example, we use the graphical method to solve for the following systems of equation. 3x plus 2y equals 18, and minus x plus 2y equals 2. We rewrite the above equations in terms of the abscissa. So we rewrite the first equation as y equals minus 3/2 x plus 9, and the second equation is y equals 1/2 x plus 1. And then we graph both equations. The first equation has a graph corresponding to this black line, while the second equation has a graph corresponding to this red line. The intersection between these two lines is at point 4, 3. X equals 4, y equals 3. This intersection is the solution to these systems of equation. If you have 3 or more simultaneous equations, each equation will be represented by a plane in 3 or more dimensions, which will be very difficult to graph. This is the downfall of the graphical method. Another problem with the graphical method are these 3 cases. 2 equations representing parallel lines, 2 equations that are coincident, and 2 equations with extremely close value of the slope. Another popular method is through Gauss elimination. Briefly, this technique eliminates one variable at a time until you end up with the solution for the last variable. You get the other variables by working your way back. This solution is actually quite familiar to you. What you would probably do with the 2 given equations is to first eliminate x1 or x2 and then solve for the other. Gauss elimination is precisely the same, but obviously more systematic. We'll see how this works in the next slide. Let's use Gauss elimination to solve the same systems of equation as previously discussed. 3x plus 2y equals 18 and minus x plus 2y equals 2. First, we rewrite these 2 equations in matrix notation. So we have 3, 2, minus 1, and 2. So 3, 2, minus 1, and 2. And then the x and y are your unknowns. 18 and 2 we write on the right-hand side of the equation. So this becomes 3x plus 2y equals 18 and negative x plus 2y equals 2. The main idea is to convert the given matrix, which is this one, into an upper triangular matrix where the diagonal elements are all ones. The first step is to divide all row elements by the first element so that all elements of the first column have values of 1. In other words, we want these values to be just 1. So in order for this to be 1, we have to divide it by 3, and in order for this to be 1, we have to divide it by 3. But whatever operation we do here, we have to do along this row. And whatever operation we do here, we have to do along this row. So if we divide this by 3, I need to divide this by 3, and I also need to divide this by 3. So I now have 1, 2/3, and 6. Now if I divide this by negative 1, I'll get 1. If I divide this by negative 1, I'll get negative 2. And if I also divide it by negative 1, I also get negative 2 here. So that's pretty simple. Step 2. Replace each element of each row, starting from the second row, with values obtained by subtracting each element in each row from the elements in the first row. Basically, what we want to do is to make this value 0. And how are we going to do that? So we subtract this from this and then put the resulting value here. What I mean is, we let 1 minus 1, which is 0, and put it here. Okay? And we do the same for all the other values. So 2/3 minus negative 2 is equal to 8/3, and we put it here. 6 minus negative 2 is 8, and we put it here. Step 3. Starting from the second row, we divide all row elements by the second element so that all elements of the second column have values of 1. So now our objective here is to make this equal to 1. Okay, and if I multiply this by 3/8, this will be 1. If I multiply this by 3/8, it will still be 0. And if I multiply this by 3/8, I'll get 3. And that's what we have here, 0, 1, and 3. And the last step is to perform back substitution. So now we have 0 times x plus 1 times y is equal to 3, or simply y equals 3. So we have already solved for y equals 3. In this first row, we have x plus 2/3 y equals 6. X plus 2/3 y equals 6. We already know y to be equal to 3. We place that here. So this becomes x plus 2 equals 6, or x equals 4. In this example, what you are going to do is to multiply the column matrix in the right-hand side by the identity matrix, as we see here. So in other words, we inserted an identity matrix on this side. Then you use Gauss elimination technique on both 2 by 2 matrices on the left-hand side and on the right-hand side of the equation without doing anything to the column matrices. In the process, the 2 by 2 matrix on the left-hand side will eventually be reduced to the identity matrix, while the identity matrix on the right-hand side will be transformed to the inverse of the original matrix. Why is that so? If we look here, we represent this matrix as A multiplied by this column matrix and equal to this column matrix. If I multiply everything in this equation by the inverse, I multiply this by inverse A and I multiply this by inverse A, this becomes an identity matrix. Okay, and this is your inverse matrix. So what we've done here is to put A on the other side of the equation. And what that does is to convert A into the inverse of A. So our objective is to make this a unit matrix or an identity matrix, and whatever happens here is our inverse matrix. Okay, so step 1 is we divide all row elements by the first element so that elements in the first column have values of 1. We've already done this before. So we divide this by 3, we divide this by 3, and we divide this by 3, and we divide this by 3. So we have 1, 2/3, 1/3, and 0. And then we divide this by -1, we have 1 there. Divide this by -1, we have -2. Divide this by -1, which is still 0, and divide this by -1, so we have -1 there. Okay, the next step is to replace each element of each row, starting from the second row, with values obtained by subtracting each element in each row from the elements in the first row. In other words, 1 minus 1 equals 0, which we put here, so that's what we have here. 2/3 minus -2 is equal to 8/3, and that's what we put here. So 1/3 minus 0 is 1/3, and that's what we put here. And 0 minus -1 is 1, and that's what we put here. Step 3. Beginning from the second row, divide all row elements by the second element. So we divide this by 8/3 so that this becomes 1. Or we simply multiply it by 3 times 8, 3/8. So multiply by 3/8, this is still 0. Multiply by 3/8 becomes 1. Multiply by 3/8, this becomes 1/8. And multiply this by 3/8, this becomes 3/8. Okay, and finally, we want this to be 0 because we want this whole matrix to be a unit matrix. So what we're going to do is to replace elements of the first row by multiplying second row elements by a number in order to null the first row element in the working column. How do we make this to 0? So what I do is I multiply this by 2/3 and I subtract this from here. 2/3 minus 1 times 2/3 is 0. And that's what I put here. So here we have 1 minus 2/3 times 0 is still 1. So this doesn't change. That's what we have here. So following the same procedure, 1/3 minus 2/3, 1/8. 1/3 minus 2/3 times 1/8, that's equal to 1/4. And 0 minus 2/3, 3/8. 0 minus 2/3, 3/8, that's equal to -1/4. See now that if we simplify this, we get to the identity matrix as expected, and we get this matrix, which we know to be the inverse matrix A. So what we need to do now is to simply multiply this matrix to this matrix here and get the result. So 1/4 times 18 plus -1/4 times 2 equals 4. Also, 1/8 times 18 plus 3/8 times 2 equals 3. This means that x equals 4 and y equals 3. The techniques in the previous slide will be taught in Physics 122 and you will perform numerous exercises. I only presented them so that you are aware of the mathematical process. In this course, what you need to learn is to implement them in a program. We now take a look at this in MATLAB and Python. So let's use the inverse matrix in MATLAB or Python to solve the following systems of equation. 3x plus 2y equals 18 and negative x plus 2y equals 2. So we have this matrix notation which represents these systems of equation. This is the matrix that we want to get the inverse of. So in MATLAB, we type it down as A equals open square brackets 3 space 2 semicolon negative 1 space 2 close square brackets. And if you enter this, you'll get this result. The inverse of this matrix is obtained simply by typing in INV open close parenthesis of A. So inverse of A. And this is the result. Now we have the inverse of A here. We want to multiply that by this column matrix here. So the inverse of A multiplied by the column matrix 18, 2 gives us 4 over 3, which is what we already expected. In Python, this is how you do it. First, you import numpy as np, and then you assign a variable A corresponding to the matrix 3, 2, negative 1, 2. And then I'm going to assign a variable B corresponding to the column matrix 18, 2. And then I perform matrix multiplication. So first I get the inverse of A, where the command is np.linalg.inverse. This is short for linear algebra. So this solves for the inverse of A, and this performs the multiplication of the matrix of the inverse of A and the column matrix B. This prints out the result in the command console of Python. One more application that we will go through is the eigenvalue problem. The solution to the eigenvalue problem is extremely useful in quantum systems such as molecular, atomic, nuclear, and solid-state physics. It basically begins with a system of equations such as the one shown above. At first, it would seem that this is just a simple systems of equation. If you take a closer look at the right-hand side, however, the constant b's are replaced by the eigenvectors x and a parameter lambda. The parameter lambda is called the eigenvalue and is unique to each of the eigenvector. Thus, the task here is to determine the eigenvalue, that is lambda, for a specific eigenvector. There is one eigenvalue for each eigenvector. We can rewrite the above equation as the one shown below. Notice that lambda is subtracted from only the diagonal elements. That is, elements with the same row and column indices. We can rewrite the previous system of equations in matrix notation as the one shown above. This is actually equal to the expression below. The solution to this set of equations is to obtain the determinant of the matrix A minus the eigenvalue multiplied by the identity matrix. Now, all of these is just mathematics, and I have not provided any attempt at providing any physical interpretation. This is because you haven't taken your quantum mechanics yet, and it will be too much to explain the physics at this point. Just take note of the mathematics and the method of solving the problem. This whole process is called diagonalization of the matrix A. There are a couple of more examples of systems of equation at the end of this slide, beginning from the next slide. We will not discuss them in this video. Please take the time to go through them and try to implement them yourself in MATLAB or Python. At this point, I hope you've learned how to handle matrices and matrix operations in MATLAB or Python, as we will be using these techniques extensively in the next two videos. See you then!